Hello, hello, hello. It's Will, February 9th, 2025. Welcome to From Bronze to GM and miniKanren, episode 2. In episode 1, I talked about this idea inspired by StarCraft series to help you level up your game in playing real-time strategy games from bronze to GM, and made the analogy to learning, how to really understand functional programming, programming languages, constraint logic programming, relational programming, from sort of a beginning fundamental level up to the point where we could do original research and communicate that to other people. Okay, so that's the idea. And we're going to get into all the technical nitty-gritty, but I think it's also important to really think about our mindset, our point of view, the philosophy, okay, that we should keep in mind, because the way a computer scientist who's an active researcher thinks, doing fundamental research, is different than, say, how a developer working in industry or an undergraduate student, how people in those other contexts are trained and incentivized to think and to work. If you're a student, from the very beginning, very young age, you are incentivized and trained to, worry about things like grades, pay attention to grades, pay attention to homework. Okay. Here is a textbook that you can read. There is a way you're supposed to learn this. The people who are teaching you this hopefully know more about it than you do. It's not always the case, but hopefully they do. And here's a book written by people who presumably knew way more about it than you do. And you can read this book, and now you will learn whatever it was that they thought you should learn to have some foundation. And then you can move on. You take tests, you do homework, all those sorts of things. And you can show your progress to other people and to yourself. And, you accumulate knowledge, and presumably if you have better scores, assuming you're doing it honestly and not cheating, then, that's a reflection of better understanding, and you can take more advanced courses and so forth. And that progression happens through undergraduate, and, even maybe through a master's degree, like a professional master's degree. But that's a very different point of view than a researcher working in an area where they're trying to work at the edge of what people know, okay? Because there, no textbook exists. If the textbook exists, they're the ones who are going to write it, okay? It's the difference between, here's the textbook, learn it, and I'm going to have to write the textbook, okay? That is a fundamentally different mindset. Similarly, if you are working as a programmer, if you're working in industry, there are lots of things for you to learn and lots of ways for you to learn it. So anyone can learn some programming. They can pick up a book. They can watch a video online. They can go to a boot camp. They can get a degree. And so programming is something like many of the topics taught in school. We have some handle on how we can teach people programming. You want to learn some Python, you want to learn some Java, great. You want to learn some basics of object-oriented programming, no problem. And then, there's things like frameworks and software engineering practices and so forth. And there are lots of ways you can go with those, lots of technology. But there's still this idea that most of the time you are going to be learning things that are fairly well understood, and using technologies like Python or Java that were developed by other people who presumably knew things you didn't, and there are textbooks on those things or videos, or you can get training. Maybe someone comes to your company and gives you training. That's happened to me a number of times when I was working in industry. Or you go and get training somewhere else. That also happened when I was in industry. There are lots of ways you can learn about the technology, but most of the time, these are things that, someone else created or a group of people created, and they documented it or other people documented it. And if you're using programming languages and programming language tools and frameworks and so forth, most of those things that you're using were things created by other people, and that makes sense, right? You don't have to reinvent the wheel. You don't have to, build everything from scratch. You're using an operating system, probably you didn't write that operating system. If you're using a text editor, you probably didn't write the text editor. If you're using a programming language, you probably didn't design the programming language. If you're using an interpreter or a compiler, you probably didn't create those artifacts yourself. When you get into being a researcher at the edge, that changes. Okay, so instead of saying, I want to build a web application and I'm going to use, 14 frameworks, and I'm going to use as much commercial off-the-shelf stuff as possible. I'm going to try to write maybe as little as possible and maybe use an LLM to fill in the details. Here, you're actually trying to concentrate more on foundational ideas. Okay, and you're building some of the artifacts at least. Now, of course, as a software engineer or developer, of course, you're writing code. But what I mean is you might be designing a programming language. You might be designing and implementing a language. You might be designing the compiler for the language. You might be designing a macro system or an interpreter or whatever. You might be trying to think about what could be different about an existing language, making major changes to it at a fundamental level. And from this standpoint, it's much more important that you can identify core, fundamental problems and techniques, things like that. That's far more important than that you're using whatever framework is currently popular in industry, or that you can save a few lines of code, because you need to really understand, identify what the problems are. You need to know the underlying theory or aspects of whatever you're dealing with well. You need to be able to do things like implement the language. And so you may be working at a smaller scale, but you're concentrating much more usually on fundamentals and on ideas and concepts. Okay, so that's very different. Today, in modern software engineering, you might be using all sorts of libraries and tools that you really don't have a good idea of how they work or how they're implemented. And they're, probably full of errors. And, who knows, you're using some library, you may not even know which language the library is written in. Maybe you're calling out to a Python library, maybe it was actually written in C++. It's just a wrapper around C++ code, and you may or may not understand the algorithms and data structures in that C++ code, and that may be fine for what you're trying to do. But when you get into the research mindset, it could be fine if it's not relevant to what you're trying to do, but if it's relevant to what you're trying to investigate and explore, it's no good. Okay, you have to abandon that and decide, okay, I'm going to, for this at least narrow area, really understand what's going on. And that might mean I have to write a compiler. It might mean I have to design a language. It might mean I have to design a macro system or whatever it is, or learn some things I don't know. I mean, I have to learn something about dependent types if I want to do this investigation and move forward. So that is a very different mindset than what you encounter as a student, at least until you're doing research, original research, or as a developer. As a developer, you're generally being paid to develop a solution to some problem. Okay. As a researcher, if you're paid as a researcher, you may be paid really to figure out what the problem is. Okay. And if you can just clarify, dig down and figure out what the problem is, that might be a huge contribution. And that might be really hard. Okay. You might be working in some area where only a few people in the world could even identify what the problem is. Whereas, for, I don't know, pick modern web development, there may be literally millions of people who could do what you're doing. You might still be producing value, but it may be, and in fact, the whole point of software engineering to some extent is for engineers to be interchangeable, okay? And if you don't think that's true, go read up about the Carnegie Mellon capability maturity model for software engineering and how that's been applied. Look at CMM level 5 organizations. That was the whole point, is that you could have these repeatable processes where the engineers could be swapped in and out. That's not true when you're in the research exploring, area. Okay, that's not, one phrase I heard. Okay, so here's a phrase. We're not making hamburgers here. That's from Tom DeMarco. Okay. I think he said that, certainly from one of his books I read. All right, we're not making hamburgers here. So if you're in a research lab, let's say, or you're acting, you're doing original research, you're not doing something that's reproducible, even in the same way that, say, doing a standard operation in medicine is reproducible. Okay, you're doing something where you really don't know what you're doing. I mean, here's another slogan. Now, whenever I'm writing down a slogan, you have to take all of these contextually and with a grain of salt, okay? Because I could write down slogans that apparently contradict each other, but they're things to think about, okay? So here's one. Where was I? I had two slogans. Oh yeah. So here are two sayings, and I don't completely agree with these, okay? But we're thinking sort of mindset, okay? From a mindset standpoint, I think they're more true than not when we're thinking about a shift in perspective. So, in science, if you know what you're doing, you shouldn't be doing it. In engineering, if you don't know what you're doing, you shouldn't be doing it. Now, there's not such a hard distinction between engineering and science, because if you're trying to do original research, sure, you're still mostly going to be building upon other people's works and artifacts and so forth, right? It's not like you have to build every single piece of equipment or every single, operating system and text editor and all that in order to do any research. So you're still going to be using lots of things that you already know about. But there'll be areas where you don't know what you're doing, okay? And that's important. And in engineering, there are going to be times where there are things you don't know. But in both cases, you're going to want to try to, fill in, at least to some extent, narrow the scope of the things you don't understand. And in engineering, you may be trying to avoid all those things you don't know. It's like, you don't know how to do something. Let's pick a different way that we do know how to do it. Where in science is you don't know how to do something. Okay, that's an opportunity to explore. Okay, so it's that part of the mindset I think is different. A couple other slogans here. I think I'm getting this quote right. The most dangerous thought for a creative person is that they know what they are doing. It's something like this, okay? This is a Brett Victor quote. And I'm hoping I'm getting the spelling right. It's something like this, okay? So if you're a creative person, you're doing creative work, you're trying to explore and play around with ideas, let's say, then if you think you know what you're doing, that's a dangerous thought, because a lot of the interesting things are going to happen when you take something you think you know how to do and then you tweak it some. And then you're asking what if questions. Okay. All right. For example, the notion of a variable in a programming language. Well, it turns out there are lots of things that we call variables in computer science that have totally different behavior and semantics. So it's a very interesting task to say, okay, here's what I've been taught or what I know a variable is. Well, what happens if we change what that means? What if we change the behavior or maybe change the very notion of what a variable is? How does that affect programming? Okay. So if you think I know what a variable is, okay, and there's only one way to think about a variable, you've immediately excluded the possibility that you could get behavior from, changing that notion. Now, of course, once again, you have to take these slogans and ideas, in the right spirit. That's not to say you should never, ever, ever use anything you've ever known about. Okay. In general, you're probably going to change one or two or three notions when you're exploring things, not everything. But we're just thinking about slogans, okay? We're just thinking about points of view and how this is a different point of view than, say, a class in high school where maybe you're drilled on some topic, okay? So here's a bunch of, math problems, here's the algorithm you're supposed to use or the procedure you're supposed to use. Now do 50 of these problems. Okay, that is a very different thing than, okay, let's try to come up with a better way of doing this. Okay, so different sort of perspective here. And part of the problem comes, I think, especially if you've been really successful, say as a student. So when I was teaching the honors intro computer science class, I noticed something very interesting is that often I was teaching students straight out of high school, and quite a few of the students, in the honors program were their high school valedictorians. So out of a class of, say, 30 people, maybe a quarter of the students or more had been their high school valedictorians, and most of the other students, maybe they weren't the valedictorian, but they were way up there. Okay. So these were people who had done very, very well in school. And that often, I think, caused a problem because I wanted to show people how they might approach problems in a creative way. But for the students who had been trained and rewarded for focusing almost exclusively on the grade point average, they were thinking coming in, okay, where's the syllabus? How many points are allocated to what? How can I guarantee that I get an A+ in this course? Before the course has even begun. And some of the students, as soon as they realized that they couldn't get an A+ in the course guaranteed, okay, they dropped the course right away. And that was their perspective, which I can understand. However, that is the opposite of an openness to exploration and playfulness and a growth mindset for the research standpoint, okay? And one professor who I've worked with, who will remain anonymous, would tell me when they were having trouble working with a PhD student, they would say, this person thinks like an undergraduate. And what that meant was, this is someone who's overly concerned with grades, who wants, the textbook to read for everything, who wants to be told the instructions, who is very afraid or very worried about failing, okay? As opposed to the mindset of let's be open-minded and play around with ideas. And, most of the things we try aren't going to go anywhere, but that's okay, because we're going to try lots and lots of things, and we will find things that are interesting, and we'll push those further, okay? So that's sort of the ironic thing, is that, say, for students, the students who do best in at least the American school system, who've been most rewarded, the valedictorians and the people who go to often very fancy schools for college, let's say, they often, I've found, are sort of fearful of being experimental and playful if they are not absolutely sure that they can get, the maximum possible grade or whatever. So that's what I mean by talking about philosophy and mindset and point of view. So what we're going to be talking about, we're going to be really trying to get up here and focused on this idea of research mentality, experimentation, playfulness, what if thinking. Okay, so we're going to have, let's call that what if thinking. We're going to try different things and say, okay, well, fine, maybe it's always been done this way, but, how could it be done differently? And in fact, one strategy I use is every once in a while, I will find something like a survey paper or a survey book that says, here are the techniques from a research standpoint. Here are the techniques you use in research. And here's, like what from the last 20 years, what people have figured out works. And if you're in this situation, you do this. And if you're in this situation, you do that. Great. That sort of thing's great because as I'm reading that sort of document, not only am I learning techniques and learning problems that maybe I didn't know about, but I'm also seeing, things from a what if standpoint, because if someone says, in this situation, you do this, and here's why. Well, from a research standpoint, the question is obviously, well, what if you didn't do that? What else could you do? Say you weren't allowed to do that. You could use anything else except that approach that has had success. Okay, then what do you do? So that style of thinking, and it's a what if thinking, and it's a constraint, maybe artificial constraint thinking. Artificial constraint thinking. That's another powerful technique where, it's sort of like the French writers who would say, okay, we're going to add a constraint, like we're going to write a novel. One of us will write a novel and you're not allowed to use the letter E in the novel or whatever. Okay. Adding some sort of constraint where even though the constraint isn't necessary strictly to solve the problem or make progress, it forces you to think about things in a totally different way where you're basically stuck right away. Like there's a way to solve the problem. And then you're saying, I'm not allowed to use the one way I know to solve the problem. Now what? Now what am I going to do? Now, if you were, if someone were paying you as a software engineer to solve their problem, and you decided, well, I've got a perfectly good way to solve the problem and would actually work great, but I just reject it for whatever reason because it'd be fun, they're probably not going to be real happy with you, okay? And I can understand why they wouldn't be happy with you. So if you're working in that sort of environment, or if you're working, if you're an elementary school or middle school student and the teacher says, okay, here you're going to do this task and do it this way, and you decide, well, I'm going to do it some totally different way, you might be rewarded by the teacher for doing that, but the teacher might also not appreciate it. So it's hard to tell, right? It depends on the people you're interacting with. If they think you're being very creative, maybe they think that's great and they give you other tasks or think that maybe you're accelerated, or they might just think you're a smart aleck and wasting their time. So that depends. But when it comes to research style thinking, I find that things like artificial constraint thinking is extremely helpful. And I'll give you an example of this. When I took an undergraduate algorithms class, I was going back to school after being a hobbyist for a long time and having a degree in special education and working in special education for a couple of years. I went back to school to get my computer science undergrad degree. And between, being sort of desperate to succeed at this job, or get a degree so I could get a job as an engineer, software engineer, and also, just my joy of programming as a longtime hobbyist, when I started at undergrad, I was, really, really serious. So I did very well in my classes, and in the algorithms class, I was the number one student. And at some point, I realized I was the number one student, but I was the number one student by like 10% or 20% or 15%. Like I could, maybe solve 10 or 15% more problems than the next student, or if it was a timed thing, I might finish 10 or 15% faster than the next student. And it was fine, but at some point, it just stopped being that interesting, okay? And I thought, okay, I want to try to challenge myself more. So I started playing a game. Whenever I was given a challenge in class, because the instructor would often give us algorithm design problems or things like that in class, I would, the game I would play is like, okay, I will quickly identify what I think the instructor wants us to do. Okay, so these are, we've learned a bunch of techniques. Which technique seems most applicable? And now I'm allowed to use anything other than that technique. Okay, I'm not going to use that technique. I can use anything else. And at that moment, in effect, I became a researcher, at least in terms of my mentality. Okay, so that was a huge change in my approach. Instead of, here's the textbook, I'll just learn the techniques and apply them in a way that they're presented to me. And it's like, okay, I went from that to, now I have to start inventing things, and I have to understand what the techniques are well enough to be able to do that. And I never really succeeded, in coming up with something totally new, a totally new algorithm. But by the end of the semester, I was able to come up with approaches where, that professor of algorithms had to consult with other professors of algorithms to try to find out if there were flaws in my approach, because I would claim I had a better asymptotic behavior. I could run my algorithms faster than, my algorithm was faster than the best known algorithm at the time. And so none of it really worked out. Okay, I never came up with some incredible new algorithm that changed the field. But I got used to this thinking process that really challenged me. Now, if I was doing homework or a test, sure, I would solve it the standard way. But anytime I had a chance, I would try to add this constraint to myself. And I think a lot of people do this with gaming, going back to like StarCraft or whatever. Like at some point you become good enough, say you're playing a video game against the computer, you become good enough that it's no longer a challenge because, those scenarios are standard. It's the same as for the class. We were basically being given standard problems. And at some point, I was advanced enough that those weren't really challenging me the same way they were at the beginning of the semester. The same with games, where at some point you probably have to add difficulty. So that's an example of artificial constraint thinking. Okay, and a great example of this in StarCraft is Fun Day Mondays. Fun Day Monday challenges by day 9. And the idea there was when day 9 was making these daily StarCraft videos, on Mondays he would issue a challenge. Okay, you're going to play games, on ladder against other humans, but you're not allowed to do things like make the core units, or you have to play with the hotkeys disabled, or you have to, put all your buildings in a strange location or whatever. And it was enough where it would change up the way you would approach the game and make you think about things differently. And sometimes the challenges were so hard sounding that they sounded impossible. Like there's no way you'll ever win a game playing with these constraints. But the whole point was to provoke you to think about things that you had already started taking for granted. Okay, that's the whole point. We don't want to take anything for granted. There may be things where, okay, we're not going to try to reinvent everything at once. So for right now, we won't, mess with this one thing. We'll just use the standard techniques. But even the standard techniques we're using, it's more like, we don't have the bandwidth to reinvent everything at once. But the standard techniques are also open to reevaluation, because it may be that in order to make progress with our research problem, we have to go back and look at one of the standard techniques and either reject it or change it. So the Fun Day Monday Challenge has a perfect example of artificial constraint thinking. And that's like really the researcher mindset. I'll give you a couple other examples. So another example was in graduate school. I took a class from Dan Friedman. That's called Advanced Dan. Some people would call it. And so it was a course that PhD students, and sometimes, even really bright undergrads, would take after you had been pretty experienced with programming languages, okay, maybe done some research and things like that. What Dan would do each week is give you a challenge. He would present some theory or topic or a paper and talk about it, and he would issue a challenge. Like, okay, so your challenge, your mission, should you choose to accept it for this week, is to do this thing. And he would either add explicit constraints, or after a while, you got a sense of his sensibilities or what he would accept as a reasonable answer. So most people are using functional programming. So if your answer, just involved a bunch of global mutable side effects, unless you could prove it was correct and things like that, he might reject that answer. But in any case, it was a series of challenges, and that was very thought-provoking, and there was original research that came out of that class. When I took the class, I added an additional level of constraint, because instead of doing everything functionally, like in Scheme, I did everything in miniKanren. And in fact, some of the things we use today in miniKanren, really came out of exploration in Dan's class. Okay. Yeah, I rediscovered things that were already known in the constraint literature sometimes. Okay, so I'm not saying that anything completely new came out of it, but even then, like a bunch of techniques and understanding that I use today came out of that class, just out of desperation, because I was like, okay, here's already a hard problem, and I'm not allowed to use Scheme, so I'm gonna have to invent techniques. Okay, so that was great. So you can think of all sorts of things, right? I'm sure you do this yourself. If you're playing a game that's too easy, do something hard. I'll give you one more example from my own personal life. Was at University of Utah, we had a games night, and so I was involved in that. And it's like grad students and whatever, postdocs, hanging out on Friday night. We'd have pizza and then games. And at some point, once again, to make the games more interesting, I would always try to add some extra constraints. So there are these card games where there's information from your cards about who you are or your group of people, and then other people know about their cards, and you're trying to either bluff or hide your information, things like that. Well, I would do things like, okay, I'm going to play the game, but I'm not going to look at my cards. Okay, so the whole game is based on looking at your cards. So I'm not going to look at my cards. I'll just bluff, and I'm going to make sure that everyone else knows I'm not looking at my cards, okay? I'm never going to touch my cards. Okay, so what does that do to the game? And so I would play these games not to win, but to explore the games, to explore the possibilities, okay? So that's another way of thinking about it. Instead of playing to win, you're playing to explore. Anyway, so that's my challenge to you, is to think about areas in your life where you've explored or played around with or added artificial constraints. Like I said, games, kids do this all the time with playing games. Like a game will get boring, so they'll change it up to make it more challenging, right? And you might do the same with homework or a sport or something like that. As soon as something becomes too easy and it gets boring, change it up to make it harder. Okay, so that's the sort of mindset we're going to rely on and try to improve and just get used to. Okay, so that means that we're going to get used to failing at doing things. We're going to get used to doing things where we might look stupid. Okay. Someone else was like, well, here's something that every first semester undergraduate learns about programming, and you can't even do it. How in the world do you have a PhD in programming languages if you can't do the thing that, we teach high school students or middle school students? But that's got nothing to do with it. Okay. Of course we could do it the standard way. The point is we're trying to come up with totally different ways of doing it. And so part of the difficulty sort of emotionally is that you open yourself up to potential criticism by people who are playing standard, let's say, okay? So instead of playing standard, we're going to play in an idiosyncratic way. And so for the people who are obsessed with efficiency and things like best practices, okay, and the engineering has to be done this way. So I've worked with computer scientists who would make claims like never use recursion under any circumstances, or if it's not done in C++ or Java, then it's not engineering. It's nonsense, okay? I've heard people make these claims. Professors make these claims. People with PhDs make these claims in computer science. We're going to have the opposite mindset, okay? So that's a difference in perspective for a lot of people to an extent that maybe they don't appreciate. Okay, so we're just going to have to getting used to, potentially being bad at things or throwing away techniques that we know work in some sense to try to find something better or at least different that has different sets of trade-offs. Okay, so that informs my whole style of thinking about things like research. And this is why, like I said in the first episode, I think that, I'm not a huge fan of Python or Java. And when I say that, what you have to understand, is from this sort of context where we're doing playful thinking and a type of experimentation where we're interested in, say, fundamentals and rethinking fundamentals, okay? It's not that Python and Java are not useful. They are very, very useful languages and ecosystems. It's got nothing to do with useful, okay? So useful is another one of these terms that we have to be very careful of. As soon as we start asking ourselves, is this useful? Or how is this useful? Then we've shut down our brains in terms of being open and playful. Okay, so we're not going to talk about useful. We're going to think about possibilities and what if. This is more like improvisation. Okay, that type of thing. And we want to say yes and instead of saying no. So anyway, this is the type of mindset that we're going to have in order to progress as a researcher. Now for the bronze, you can get pretty far. Bronze and silver and gold, you can get pretty far without having that mindset. But if you want to get to the point where you're innovating, you're doing the things that other people are going to copy in the future, you have to have a different sort of mindset. Okay. So remember, we're going from reading the textbook, or in bronze, we didn't even read the textbook. Maybe in silver, we read part of it, and in gold, we read the textbook. We're going from that to, we'll have to write the textbook once we figure out what in the world we're doing. Okay, so in fact, that's not even necessarily Grandmaster. It's like Super Grandmaster or, Korean Code S StarCraft Pro who's changing the metagame or whatever it is. We want to get up to here. If it's martial arts, you have white belts and brown belts and stuff like that. We don't even really want to be a black belt. We want to be a red belt. We want to be someone who is, inventing their own school of martial arts or inventing totally new techniques that other people want to come and get their black belt under us. Okay, that's what we're trying to get towards. Now, it might take us a long time. Okay, and given how many things there are to know in the world, we're going to be, in some sense, just limited by the amount of time and effort and attention we have in terms of areas in which we can innovate, but that's where we want to be going. Okay. So you can get bronze, gold, you can get a certain level without having this playful thinking. But you're not going to get to, super GM level if you're not really experimenting and playing around with things. You're not going to get to the point where other people want to copy, other pros want to copy your style. Okay. That's what we want to get to. So that's the philosophy. Okay. That's the philosophy. And another part of this philosophy is, getting unstuck and, taking responsibility and initiative for our own learning. Okay. And here's something I've seen both in universities and also in industry when I worked in industry. I've seen people in industry who had degrees in computer science from schools you've heard of and who were in senior development positions or even lead developer positions who didn't understand recursion, and they were afraid of recursion. Recursion intimidated them, and they've been working in industry for a long time. Or things like students and people in industry who, if they had to use a feature of the main programming language they were using day in and day out, they just got stuck. And, I'll see when I worked in industry, senior developers, having arguments with each other that were like, I think it works like this. No, I think it works like this. And after a while, if I saw one of those disagreements, let's say it's about Java, I had the Java spec on my desk. I had the Java tutorial on my desk, and I'd look up the feature. I would write a little example program to try it out, maybe a couple of examples to test out the behavior, look at the specification. I was not intimidated by reading the specification. I knew my way around those things well enough, and I knew how I could write a little program very quickly to test out the behavior. And I would say, okay, let's have a timeout in this fight. Here's what I found. And that would almost always resolve the fight. But what would happen is the next week they would have a different argument about another language feature, and it never occurred to them that they could do the same thing that I was doing. Okay. Now, maybe just socially they enjoyed, arguing about it. I don't know. But I noticed that I never saw them do the same thing. I never saw one of them say, okay, let's stop a minute and just figure it out. Similarly with undergrads and even with seniors, I would see seniors taking, say, a programming languages class, and they would encounter some feature of a programming language used in the class that they didn't know, and they would just stop. They would say, well, I'll wait until next week and I'll ask the teacher, or I'll wait until lab and ask the teaching assistant, or whatever it was, or I'll email the teaching assistant, and just find out how it works. And instead of doing that, I would always say, well, have you looked at the documentation? Have you looked at the tutorial? Have you tried writing a couple test programs to see how this thing works? And the answer was always no. And what I found was, by the time someone got to be a senior in college, or by the time someone had been working in an industry for a long time, it was way too late in general to get them to change their mind about, how do you learn a feature of a programming language? They had never learned how to learn these things on their own. Okay, so there was a type of meta learning where they had to learn how to read a specification, or they had to learn how to write little example programs, or at least, decide what is a good example program, what is the feature I'm trying to explore, and what's a program I can write that's short that would explore it. Look at the spec, look at a tutorial, all those things. And within, 10 minutes know the answer to the behavior, or maybe half an hour, okay? But being able to do that. So when I started teaching the honors undergrad courses, that was something I really focused on. It was like, okay, we're going to look at the specification for this programming language and the documentation, and here's how to learn about a feature. And what I would do is, over the course of the semester, give less and less help, direct help for those things. And I would say, okay, have you read the spec? Or have you looked at the tutorial? And if the answer was no, then I wasn't going to help them until they had done so. So that's what I mean by taking initiative and responsibility for your own learning. That's another really, really important mindset. Okay. And if you're going to work at the frontiers of knowledge, if you're going to work at some area where there are no textbooks, you better get good at this. You'd better, take responsibility in getting unstuck and develop strategies for getting unstuck. And you better take some initiative, right? Now, it's not that you can never ask for help or talk to another researcher. Of course you're going to do that. But, if you're really at the edge, then there aren't that many people you can ask necessarily, and they're all busy with their things. So they might not understand it better than you do. You probably understand it better than they do. So you're just going to have to get used to taking initiative and responsibility. So that's one of the things we're going to do is, when we're learning Scheme, I'm not going to show you Scheme like I was showing, like I had showed, say, like someone in a programming boot camp who, is trying to get out as quickly as possible so he can get a job in industry. Like, I probably wouldn't show that person Scheme at all, to be honest, if that was a situation. So instead, I'm going to show you Scheme in such a way where we talk about foundational ideas, because we're going to be talking about ideas a lot. And in addition, I'll be showing you resources, and we can look things up in the specification, look things up in the main documentation, all those, write little example programs to try out the behavior. Those are all critical skills. You have to have that, because if you can't learn Scheme, even though there's a zillion textbooks and tutorials on it, how in the world are you going to get unstuck when you're working at something where maybe you're the only person in the world who understands that problem or is capable of understanding that problem, without other people leveling up and learning about your very, very specific narrow research interests? Okay, so that's an important perspective. Okay, we're going to have to be we're going to have to be able to rescue ourselves when we get in a jam. Okay. Yeah. So anyway, that at a high level is the type of mindset we need to have. One that's playful, experimental, what-if thinking, more like improvisational. Things where we're going to think about constraints and how we can add constraints to enhance our creativity. We're going to rethink things that we've taken for granted. Okay. Here's one more saying, and I don't know. Okay, so as far as I know, this one's anonymous. Okay, there's another one which is, I'm trying to remember exactly how this goes. It's something like in science, a discovery, the reaction that leads to a discovery is more often, that's funny, than eureka. Okay. Yeah, every once in a while you make some discovery and you're like, oh, I figured it all out. But usually it's more like, well, that's weird. Okay. And that's another part of this style of thinking. If we see something weird that we don't understand, we're not going to sweep that under the rug. Okay, that means that either we don't know something about, say, the language we're using, okay, in which case we need to take responsibility and initiative and figure out what's going on so that we don't build on a foundation of sand. Or we found something really, really unusual that maybe leads us to new insight or a new way of thinking about things. So, we have to look out for that. We're not going to, we're not going to cover over the weird behavior we see. Okay, like if you're an engineer and you see something that's funny, if you're pressed for time, you might say, okay, let's use a totally different approach because we don't have time to de-risk, or assess what the risk is. But as researchers, if we see that's funny, at a minimum, we need to note that and come back to it if at all possible. But it's much better if we can just stop right there and really investigate it. Now, for engineering also, I think that would also be, you'd want to understand that's funny. So often in engineering, there are things like testing physical components to destruction, where there's a model that tells you when a component should fail. Okay, if the component ends up being twice as robust as predicted, the engineers aren't happy. That means that their predictions are not right. They're unable to predict the behavior of things. Yeah, sure, if they over-engineered it intentionally to be twice as strong as necessary, that's different. But if they think it's going to fail at a certain point, and they're wrong by a factor of 2, that's not, cause for celebration. That means like they don't really know what they're doing. They need to figure out what's going on. Are they using the materials they think? Whatever it is. So anyway, we are going to look for that's funny moments. And if there's something we don't understand, we're not just going to move on. We want to figure out what that's about. So this is sort of philosophy, the mindset, point of view that we have to embrace to get up to here. Okay. Now, if we just wanted to learn some scheme, it wouldn't be necessary. Okay. If we just wanted to do programming, Alan Kay had this saying that when he went to grad school, he didn't know anything. All he knew was how to program. All right. Now, if you're in industry, that doesn't make any sense because you can make a very good living off programming. However, if you're thinking about in terms of a research and discovery and pushing the horizon, pushing the frontier of knowledge, then it makes total sense because just knowing how to program is not the same thing as making innovations. Okay. So you need to know other things in order to get to the point where you're making innovation. So that's the sort of perspective we're going to have. So I'm not just going to show you scheme and miniKanren. I'm going to show you them in a way and talk about them in a way and explore things in a way where we can get up to the point where we can do innovation and we can communicate things we discover or learn and understand what other people have found and build on it and experiment with it. Okay, so that's the whole point. And it's a different mindset than being an A+ student. And it's a different mindset than learning a skill that gets you, a raise or a promotion. Okay, so that's the perspective we're going to take, and that may or may not fit what you need in your life right now. Okay, but I want to be very upfront about this. And if you're coming to this series from a standpoint of I am going to be valedictorian and I have to get an A+ and everything, I can never fail, then at least within the context of this series and what we're talking about, I ask you to leave that behind, okay? For this little piece of time, if you want to learn how to do research, original research, you have to be open to failing and open to not knowing what you're doing. And the same with, if you're working in industry, okay? You might say, well, Will doesn't know the latest JavaScript framework. Well, that is almost certainly true. But whatever the hot JavaScript framework is 10 years from now is going to be different. Even if it's the same framework, it'll be so different, may as well be different, totally different. But the lambda calculus won't be different 10 years from now, okay? So we're going to concentrate on things that are fundamental, things like math and logic and semantics and foundations that are not changing quickly. Okay, so that's how we're going to look at things. and we're not going to talk about what's useful, and we're not going to talk about what's hot or what's going to get us a job, or IPOs or alpha or individual contributors or, pull requests or, agile or whatever it is. Okay. You think Bitcoin, blockchain, whatever those things are, they're going to exist outside of this world. Okay. And if you can figure out how to apply these things to those other things, well, great, because a lot of this is applicable if you're at all creative. But that's not what we're going to be concerned about here. So we're not going to talk about utility and usefulness. Those are not our primary concern. Okay. Difference in perspective. So yes, I'm going to show you how to program in a certain way and how I think about programming. But the point isn't to learn how to program. The point is to get to the point, get to this area where we have, a language of discourse where we can think about fundamentals and experiment and implement things that are different. So we can do our playful, open-minded thinking and play around with artificial and real constraints and all that. Okay, so that's the whole point. All right, so I've gone on for a while and I've tried to hit this over and over and over again. Maybe I overdid it. In my experience, I probably didn't. And for at least the people who really need to hear this, it's going to be hard for you to change this mindset. Okay, if you're really coming in from the mindset. And like I said, a lot of people who have been extremely successful in school, have this mindset ingrained to a level they can barely see themselves. Okay. So anyway, that's it for this talk about philosophy and mindset. We'll move on next time and start getting into technical details and start looking into scheme. But important to understand. So, if someone says, well, are you going to talk about blockchain, or are you going to talk about, can you do everything in Python, to make it more accessible? It's like, no, I'm not going to do it in Python. Python is irrelevant to what we're trying to do. We're trying to do fun foundations. Okay. We're going to do things close to lambda calculus, stuff like that. Python doesn't look very close to lambda calculus. It's full of design decisions that maybe make it useful for someone to read the code. Maybe it's nice to read it and it kind of reads like English pseudocode, but that's not what we're going to optimize for. We're going to optimize for ideas and for easy experimentation and play in a certain way for which, Python in some cases would be really good for, but in many other cases, the cases we're going to explore, probably not as good a language as Scheme, let's say. Okay. So when I do these things that might seem bizarre, I just want you to know where I'm coming from. Okay. It's not like I haven't thought about these things or I've never programmed in Python. This is actually very, very thoughtful over a long period of time, but it may not be clear unless, I'm explicit about it. This is true a lot, for example, in an intro programming class. I've seen plenty of people coming into maybe an honors class and, they've been programming for years, and they see some older professor using some weird language for functional programming or something. And they think, well, this person doesn't know anything. They're probably just reading it for some textbook. It's like, well, that person might actually know an awful lot, but they may not have the time or the interest in going into really detailed explanation of why they made those particular decisions. But it usually comes down to, going into fundamentals. So that's the mindset we're going to, okay? And then once you understand these ideas, sure, you can do it in Python or Java or, whatever language you want. But we're going to concentrate on ideas and playing with ideas, and, everything's going to be optimized towards that, okay? So from that standpoint, Java is irrelevant. Python is irrelevant. Scheme is really irrelevant as well. It's just we have to pick a language, and Scheme is a language where I am very familiar with playing with ideas in it, and it's small and easy and malleable, it's easy to change. Okay, so there's not much to get in your way. So that's why we're choosing it. Okay, but it's like not really about scheme, and it's not really about miniKanren either. It's about ideas like relations and ideas like constraints. Okay, so yeah, we just have to pick some choices, and all the choices have trade-offs. But we're going to concentrate on ideas and high-level thinking and experimentation and openness and creativity, playing around, okay? So that's a different way of thinking than we often think in our everyday lives, okay? And including for me as, a working computer scientist, I often don't get to play in this area, There are always other types of things we have to think about in life and programming and so forth. But for this series, we're going to think high level ideas, playful, okay, and learning how to get unstuck and taking responsibility for our own learning. Okay, there we go. Enough said about that for now, at least. This is something this is like a practice. Okay, this way of thinking is a practice. It's not like you just like instantly get it. It's a way you have to constantly, practice it and work on it. You get better over time. And if you don't, use it, then I don't know if you lose it, but it's something you have to practice to get the benefits of it. Okay. So if you're not doing this, at some point you get used to thinking this way. It's not like you're going to forget how to do it, I don't think, but it's more like you have to practice this on an ongoing basis to get the benefit of it. Okay, if you want to discover something new, you actually have to be thinking about it, and that's thinking about it at the right level. All right, so that's enough of this. In episode 3, we'll start getting into scheme, but just keep in mind, it's all going to be like this. Okay, we're learning scheme not to learn programming, but to be able to explore ideas. Okay. Have a good one, and hope to talk to you soon. Bye-bye.